Hello students, welcome to grade 12 chemistry revision lesson on atomic structure and the periodic table. In our today's lesson, we will learn about atomic spectrum, the Bohr model of the hydrogen atom and the quantum mechanical model of the atom. At the end of this lesson, you will be able to list the Bohr theory, calculate the de Broglie wavelengths, tell the Heisenberg's uncertainty principle, list all possible sets of quantum numbers of electrons in an atom. Students, if you are ready, then we will get started. Atomic spectra. Atomic or line spectrum are produced from the emission of photons of electromagnetic radiation or light. If an atom is vaporized, thermally or electrically excited, then it emits a light with a discrete frequency. Now, if this light dispersed by a prism, if this light is allowed to pass through a prism, we observe a line spectrum rather than a continuous spectrum. For example, excited hydrogen atom produce a line spectrum. You see, this is line spectrum or emission line spectrum. Sunlight, a normal filament light bulb, and a yellow sodium straight light produce a continuous spectrum. If any white light is allowed to pass through a prism, it produces a continuous spectrum, one color merging to the other without gap. The Bohr model of the hydrogen atom. Niels Bohr, who worked with Ernest Rutherford, he was a Danish physicist. Niels Bohr suggested that electrons are revolving around the nucleus just like planets revolving or moving around the sun. What are the postulates of Bohr model? Postulates 1, as long as an electron stays in a given orbit, it neither gains nor loses energy. What does this mean? The accelerating electron does not emit energy in the form of radiation when it moves on one of the allowed circular orbits called stationary states. 2, when an electron jumps or moves from one orbit to another, it either emits or absorbs energy. You see, when an electron moves from one orbit into another, it either absorbs or loses energy. The energy emitted when an electron moves from higher energy orbit to a lower energy orbit. The energy is absorbed when an electron moves from lower energy orbit to higher energy orbit. This is the second postulate of Bohr model. 3. The energy of an electron is proportional to its distance from the nucleus. The farther the electron is from the nucleus, the more energy it has. You see, the farther the electron from the nucleus, the more energy it has. This is the third postulate of Bohr model. Number 4, only a limited number of orbits with certain energies are allowed. In other words, the orbits are quantized. Orbits are quantized, you see. N equal 1, N equal 2, N equal 3, and so on. Example, calculate the energies of the states of the hydrogen atom with N equals to 2 and N equals to 3, and calculate the wavelengths of a photon emitted by the atom when an electron makes a transition between these two states. Solution. We know that energy of an electron at each orbit is calculated by using the formula energy En equal minus 2.18 times 10 raised to minus 18 joule divided by n square. Therefore, energy of an electron in the second orbit, n is equals to 2, is E2 equal minus 2.18 times 10 to the power of minus 18 joule divided by n square, which is t square 4. Energy of an electron in the third orbit is E3 equal minus 2.18 times 10 to the power of minus 18 joule divided by n square, which is 3 square 9. This is energy of an electron in the second orbit. This is energy of an electron in the third orbit. When an electron make a transition from the third energy level to the second energy level, energy is emitted in the form of light. Now this energy, the change in energy, delta E equal E final minus E initial. An electron make a transition from the third energy level to the second energy level. Now the final energy is E2 minus E3. Energy of an electron in the second orbit is this minus 2.18 times 10 to the power of minus 18 joule divided by 4 minus energy of an electron in the third orbit E3 is minus 2.18 times 10 to the power of minus 18 joule divided by 9. Minus become plus 2.18 times 10 to the power of minus 18 joule divided by 9. Now the change in energy delta E equal change in energy is 3.03 times 10 to the power of minus 19 joule. This is energy emitted when an electron make a transition from third energy level to second energy level. You are asked to calculate wavelengths of a photon emitted. Now, the change in energy delta E equal h times frequency is speed of light divided by wavelengths. From this, wavelengths of a photon delta, wavelengths of a photon equal h times c divided by change in energy. H is Planck's constant having a value 6.626 times 10 to the power of minus 34 joule second divided by change in energy is 3.03 times 10 to the power of minus 19 joule times speed of light speed of light is 3 times 10 to the power of 8 meter per second. Now this gives wavelengths of this photon is 656 nanometer. 656 nanometer. This is wavelengths of a photon emitted when an electron make a transition from the third energy level into the second energy level. Lewis-de Broglie equation. The Lewis-de Broglie equation enables us to calculate wavelengths of particles. Using Einstein's equation, Albert Einstein derived a famous equation which is energy equal m times c square. The significance of this equation is that energy has a mass. Again, Planck's equation for an energy, delta E, change in energy, delta E equal h times frequency equal Planck's constant times frequency is speed of light divided by wavelengths. We can equate the two equations. This is Einstein equation. This is Planck's equation for energy. Now, m times c square equal hc divided by wavelengths. C will be cancelled by c. Now the wavelengths lambda equal h divided by mass times c equal h divided by m times for a particle moving with a speed v. C become v m times v. Lambda equal h divided by mass times velocity is de Broglie's equation, which enables us to calculate wavelengths of particles. This is de Broglie equation. De Broglie equation. Using Einstein's equation and Planck's equation for energy, de Broglie proposed that a particle with a mass m moving at a speed v has a wave nature. You see, wave nature, because wavelengths is the property of a wave. Wave nature consistent with a wavelength given by wavelengths equal h is Planck's constant divided by mass of a particle times v is velocity of a particle. Lambda equal h divided by mass times velocity is de Broglie's equation. For example, what is the characteristic wavelength of an electron in nanometer that has a velocity of 5.97 times 10 to the power of 6 meter per second? Mass of electron is 9.11 times 10 to the power of minus 31 kilogram. You are asked to calculate wavelengths of an electron. We have this wavelengths of an electron equal h divided by mass of an electron times velocity of the electron. H is Planck's constant having a volume 6.626 times 10 to the power of minus 34 joule second divided by mass of electron is 9.11 times 10 to the power of minus 31 kilogram. 31 kilogram times velocity of the electron is 5.97 times 10 to the power of 6 meter per second. Now, what is the relation between joule and kilogram, meter and second? We know that work by definition is force times distance. Work equal force is mass times acceleration times distance. The units of work is joule. Therefore, 1 joule equal mass, its unit is kilogram. Acceleration, its unit is meter per second square times distance, its unit is meter times meter. Therefore, 1 joule equal kilogram meter square per second square. This is the relation between joule and kilogram meter square per second square. Now, 6.626 times 10 to the power of minus 34 joule is the same as kilogram meter square per second square. Kilogram meter square per second squared times second divided by 9.11 times 10 to the power of minus 31 kilogram times velocity of the electron is 5.97 times 10 to the power of 6 meter per second. Now, wavelengths of an electron, lambda of an electron equal this divided by this is 0.123 meter. 0.123 meter is wavelengths of an electron having mass 9.11 times 10 to the power of minus 31 kilogram, moving with a velocity 5.97 times 10 to the power of 6 meter per second. The quantum mechanical model of the atom, macroscopic objects or large objects do exhibit a wave-like motion because wavelengths of a particle equal h divided by mass times velocity. But the wavelength is too small, you see. For large objects, for microscopic objects, their mass is large. Wavelength is inversely proportional to mass. Is too small for human to perceive. For example, an electron traveling with a velocity of 7.3 times 10 to the power of 7 meter per second, its wavelength is this, you see. Because wavelengths of an electron equal h divided by mass times velocity. H is Planck's constant, which is 6.626 times 10 to the power of minus 34 joule second, divided by mass of electron is 9.11 times 10 to the power of minus 31 kilogram, times velocity of the electron is this 7.3 times 10 to the power of 7, which is 9.96 times 10 to the power of minus 12 meter is wavelengths of an electron. This is macroscopic object, large object, you see. Its mass is 1.5 kilogram, traveling with a velocity of 2 meters per second. Now, wavelengths of this ball, wavelengths of the ball, lambda of the ball equal h divided by mass times velocity. H is Planck's constant, having value this, divided by mass of the ball, which is 1.5 kilogram, times velocity of the ball is 2 meters per second. Now the wavelength of the ball is this, 2.21 times 10 to the power of minus 34 meter. Now compare the two wavelengths, wavelengths of the electron and wavelengths of the ball. Wavelengths of the ball is too small, you see. Therefore, the wavelengths of the ball is too small to be detected. Electrons are macroscopic particles which move with a very high speed. As a result, it is very difficult to trace the exact location of an electron around the nucleus. Note that it is very difficult to pinpoint, to indicate the exact position of an electron. Therefore, an orbital describes a region in an atom that has a high probability of having an electron or high electron density. An orbital is a particularly shaped volume of space where the probability of finding an electron is high. The Heisenberg's uncertainty principle. According to quantum theory, it is impossible to know the exact position and momentum of an electron at the same time. This is known as the uncertainty principle. According to uncertainty principle, it is impossible to indicate, to know both position and momentum of an electron simultaneously. Therefore, The Heisenberg's uncertainty principle states that it is impossible to know simultaneously both the momentum and speed of an electron exactly. The products of the uncertainties in both the position and the speed of a particle was inversely proportional to its mass. Now, from the Heisenberg's uncertainty principle, change in position times change in momentum is greater than or equals to h divided by 4 pi. Change in position times momentum is mass times velocity. Therefore, mass times change in velocity is greater than or equals to h divided by 4 pi. H divided by 4 pi. For example, calculate the uncertainty in position for an electron in a hydrogen atom if the electron velocity is known to be within 10% of 2.2 times 10 to the power of 6 meter per second. Mass of electron is 9.11 times 10 to the power of minus 31 kilogram. You are asked to calculate the change in position, uncertainty in position. Now, from the Heisenberg's uncertainty principle, we have this: the change in position times mass times change in velocity or uncertainty in velocity equal h divided by 4 pi. From this, the change in position or the uncertainty in position delta x equal h divided by 4 pi times mass times change in velocity. H is Planck's constant having value 6.626 times 10 to the power of minus 34 joule second divided by 4 times pi is 3.14 times mass of the electron is 9.11 times 10 to the power of minus 31 kilogram times change in velocity. Velocity of an electron is what? 10% of this is a change in velocity equal 10%. 10 over 100 of 2.2 times 10 to the power of 6, which is 2.2 times 10 to the power of 5 meter per second. Now the change in velocity is 2.2 times 10 to the power of 5 meter per second. Now the uncertainty in position delta x equal 5.6 times 10 to the power of minus 10 meter. This is uncertainty in position delta x. Quantum numbers. According to quantum mechanical model or quantum mechanics, each electron in an atom can be described by 4 quantum numbers. These are the principal quantum number, the azimuthal quantum number, magnetic quantum number, and spin quantum number. The quantum mechanical model describes the probable location of electrons in an atom by describing principal energy level, energy sublevels or subshells, orbital in each sublevel, and spin of the electron. There are 4 quantum numbers. These are the principal quantum number denoted by the symbol n, having value 1, 2, 3, and so on. The principal quantum number n indicates the relative size and energy of atomic orbitals. The larger the value of n, the larger the orbital. Look, this is n equal 1. 1 is atomic orbital. This is n is equals to 2. 2 is atomic orbital. 3 is atomic orbital. 4 is atomic orbital. The larger the value of n, the larger the orbital. The larger the value of n, the higher the energy. As the value of n increases, energy also increase in energy. Number of orbitals is equals to n squared. Maximum number of electrons in an orbital is 2n squared. For example, if n is equals to 3, number of orbitals is equals to n squared, which is 9. There are 9 orbitals in the third energy level, in the third principal quantum number. What are these? N is equals to 3, 3s, 3p, 3d. You see, s subshell has one orbital. P subshell has 3 orbitals, px, py, and pz. D subshell has 5 orbitals. 1, 2, 3, 4, 5. Total 1, 2, 3, 4, 5, 6, 7, 8, 9. Therefore, the third energy level, n is equals to 3, has 9 orbitals. Maximum number of electrons in orbitals. An orbital accommodates a maximum of 2 electrons. Therefore, the 9 orbital accommodate a maximum of 18 electrons. 2n squared. Calculate the number of orbitals and maximum number of electrons in the fourth shell. N is equals to 4. Maximum number of electrons in the fourth shell. Number of orbitals is equals to n squared. 4 square is 16. You see, the fourth energy level have 16 orbitals. What are these? 4s atomic orbital. You see, 4s atomic orbital, 4p atomic orbitals, 4d atomic orbitals, and 4f atomic orbitals. S subshell has 1 orbital. P subshell has 3 atomic orbitals. D subshell has 5 atomic orbitals. F subshell has 9 atomic orbitals. Total 16. Each orbital accommodates a maximum of 2 electrons. Therefore, the fourth energy level, total number of electrons in the fourth energy level, total number of electrons in the fourth energy level equal 2n squared, which is 2 times n squared is 16, 32 electrons. The azimuthal quantum number, denoted by the symbol L, is also known as angular momentum or subsidiary quantum number or orbital shape quantum number. It gives the shape of orbitals and number of subshells present within any shell. Having an integer values from 0 to n minus 1. The azimuthal quantum number take values from 0 to n minus 1. If n equals 3, if n is equals to 3, L equal 0 to n minus 1 equal 0 to n is 3, 3 minus 1 is 2. 0 to 2 means L equal 0, 1, and 2. L is equals to 0 is S subshell. L equals to 1 is P subshell. L is equals to 2 is D subshell. Having an integer values from 0 to n minus 1. It gives the shape of orbitals. We know that S subshell, spherical in shape. P subshell, dumbbell in shape. Therefore, the azimuthal quantum number indicates shape of atomic orbitals. Example, determine the value of L if the value of n is equals to 3. If n is equals to 3, n is equals to 3, the possible values of L are L equal from 0 to n minus 1, 0, 1, 2. L is equals to 0 is S subshell, L is equals to 1 is P subshell, L is equals to 2 is D subshell. If n is equals to 4, the possible values of L are from 0 to n minus 1, 0 to 3, 0, 1, 2, 3. This is S subshell, this is P subshell, this is D subshell, this is F subshell, SPDF. The magnetic quantum number denoted by the symbol ML is also known as the orbital orientation quantum number. Magnetic quantum number, also known as orbital orientation quantum number. It is an integer having values from minus L through 0 to plus L. It prescribes the orientation of the orbital in three-dimensional space about the nucleus. For example, if the value of L is equals to 4, then the possible values of ML are from minus L through 0 to plus L. If L is equals to 4, then ML from minus 4 to plus 4, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4. It indicates number of atomic orbitals. Yes, L is equals to 4 is G subshell, G subshell. How many orbitals are there in G subshell? 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 orbitals in G subshell. G subshell. The electron spin quantum number denoted by the symbol MS. The spin quantum number take values either plus 1 over 2 or minus 1 over 2. It indicates direction of electrons. For those electrons open upward, the MS value is plus 1 over 2. For those electrons open downward, the value of MS is minus 1 over 2. Therefore, the spin quantum number indicates direction of electrons, electron direction. Students, in our today's lesson, we learned about atomic or line spectrum. As we said, when an atom is vaporized, thermally or electrically excited, it emits a light with a discrete frequency. If this light is allowed to pass a prism, it produces a line spectrum rather than a continuous spectrum. We also discussed postulates of the Bohr model. We discussed the 4 quantum numbers: the principal quantum number, the azimuthal quantum number, the magnetic quantum number, and spin quantum number. This brings us to the end of our today's lesson. Until next time, goodbye.